I'm Jamie Burkhard. I'm a grad student at Loyola Marymount University in the Environmental Sciences program. And I just finished a project on measuring the efficiency of biofiltration systems. So we specifically looked at one right near the Ballona Creek. So to introduce this topic, sorry, some of you can plug your ears if you don't want to hear anything about climate change, but we are going to be going through some, obviously, impacts from climate change that are going to be exacerbated by any temperature fluctuations like that. And primarily in these two main categories, for runoff and for drinking water supply. So for runoff, which is where my project focused primarily on, it can be seen in increased runoff flows, so different flashier kind of storms that are coming through, contaminated coastal waters, and then impacts to marine life and recreation in addition to that. So one of the best ways I think that we can help to combat these kinds of problems is with low impact development. And the EPA's definition of low impact development are things that kind of mimic natural processes. So basically using what nature does on its own that we've started to maybe move away from and kind of get back to that. So to protect water quality, you should be focusing on infiltrating runoff, which we've mentioned earlier today, which was awesome to hear. And it can increase groundwater supply, which is also really important, especially in coastal areas, so that we don't get that saltwater intrusion. And it can help reduce the impacts of the contaminated runoff downstream. And the next thing that I was going to talk about is that it realizes many ecosystem services that I think a lot of people tend to overlook. So these are things that Mother Nature provides for us for free, no cost to us. It's doing a great job of giving us food, fresh water, wood, regulating the climate, flooding, and these are the things that my project focuses on, and I really wanted to bring the attention also to the aesthetic, spiritual, educational side of it as well, because as many of you have already said, it's not solely about the science. The important thing is really being able to bring the science to the people in really actionable ways, and we can really make a lot of difference with projects like this because there's huge benefits to communities that are not having a lot of green space near them, or there's a lot of health benefits. There can be educational opportunities for schools in that area, so a lot of benefits. So biofiltration systems are essentially exactly what it sounds like. It's using living material to filter out pollutants in the water, capturing and infiltrating runoff, and it's really a key aspect of the low impact development toolbox, and one of the best things about it is that you can scale it up or down. My project is pretty large, but it's something that you can do as tiny as something in your front yard or as huge as a university campus. So these are just a couple examples. So the picture on the left is a Green Street example, and the picture on the right is actually our rain garden in Culver City, and it's kind of filling up during a storm. So a snapshot of the creek that we looked at. Ballona Creek, the difference between the dry and the wet weather flows is about a factor of 10 difference, so 16 versus 162 MGD. That stream, or that creek, has identified the main runoff contaminants are fecal indicator bacteria, pesticides, metals, and trash, and those were identified as the TMDLs that they need to work on improving. This is a map of where the garden is located. So as you can see, there's actually two little strips right there on the left side of the creek and the right side of the creek if we're looking down on it. The right side of the creek is the more commercial side, and that's where our project is located. There is a smaller version of it across the creek and right near the bike path over there, but that is more of a residential area and hasn't been looked at yet. So this study is on the south side of that rain garden and located within Culver City, so we're getting that Ballona Creek before it goes out into the wetlands and then eventually to the bay. This is the configuration of the garden. So it was originally constructed in 2011 by the Bay Foundation. It was modified in 2014 some enhancements were made. They needed to build some more of the wall needed to be restructured a little bit, and adding a couple really huge boulders to help really slow down that water flow. It's 300 meters long and 3 meters wide, so a total of 900 meters squared. It collects runoff from about 11 acres of land in a commercial light industrial, I would say, area around it. It's designed for a 3/4 inch storm, so meaning it's designed to capture 3/4 inches of rain, and then anything above that kind of gets diverted back out into the creek. It has native vegetation, large cobble boulders to dissipate energy. There was some watering involved when it was first planted to kind of really get the plant started, but as of now it's not being watered or irrigated by anything, so there's no extra water that's being added to it other than just dry weather flows from the surrounding areas. So as you can see here, we have 5 different inlets and 2 outlets. So the 5 inlets are allowing water to come in through the garden. All of them are really right off of parking lots, so there's a great structure, and then it actually is coming up through the garden, so it's moving up, and has some teed pipes through there so that it's not all coming up in one area, because we really want to slow the flow of the water down. So we're building the level of the water up until it reaches the level where our outlet structures are located, and then it falls into the outlet structures and is discharged back out into the creek. So that's what happens whenever we reach capacity in the garden. The pollutants that we measured were fecal indicator bacteria, E. coli, and enterococci, total suspended solids, metals like copper, zinc, and lead, polyaromatic hydrocarbons, and then both diesel and gas hydrocarbons. The thing that I wanted to point out here is that we were actually able to do the first 3 categories on campus at LMU with a lot of help from the different labs that are in the area. We actually measured both the fecal indicator bacteria and the total suspended solids with the help of our student volunteers. So we were continually going out to sample during our rainstorm, coming back to the lab and actually doing the analyses, because the bacteria especially has to be done within that first 6 hours after you've collected the samples. And then we'd go back out and collect more samples and then come back and do more lab work. So it was a lovely little back and forth. And the metals were done on the lab right down the hall from us on the ICP-MS. And so the only 2 that we actually had to send out to be done were for the organics. So those were sent down to the Hermes lab at Cal State Long Beach that the Bay Foundation uses. One of the most important aspects of this project was trying to measure flow within the garden. So how we were able to do that is with these really specially constructed weirs. Each one was built specifically for that inlet or outlet that it was going into. None of them are the same, so they were each had to be built very specifically for that area. And as I said, so we have 5 inlets and 2 outlets, so there's 7 of them total. And using that V-notch weir at the bottom picture right there is how we funnel the water through. And then the white PVC pipe that's right next to it is holding a Hobo water level logger. No, I didn't name them. It's an onset proprietary technology. So it is taking 1-minute intervals of the temperature and pressure. And as you can see in that far right upper hand picture, not only do we have one inside each one of these white PVC pipes, but we have one at our area, we call it the courtyard because it kind of looks like a courtyard, that's out in the atmosphere, and it's taking the 1-minute interval readings of the atmospheric pressure as well. So then we're able to kind of subtract the atmospheric pressure and only see the pressure that the Hobo unit is measuring from the water flow right in that V-notch weir section. These are all of our beautiful calculations that I'm sure everyone is thrilled to see. So as you can see, the V-notch weir that I talked about, really it depends on the height of the water as it's going through that V, and we just have these calculations in a beautiful Excel spreadsheet, and input our readings from the hobo units after we go out and collect them, and then we're able to actually translate the head, so the water height, into flow information. So, sampling, lab work. This was actually done over 2 seasons, so this was a 2-year study. There were 4 storms that were collected the first year in 2015-16, and this year we were actually able to get 5 storms, 2016-17. The hydrographs were created using our flow data for the first year for every one of the storms that they sampled, but this year we actually were out there, I was out there putting those hobo units out every time that we were going to get a measurable amount of rain, and as a result of that we were actually able to get 28 different hydrographs produced for this rainy season. So we were able to get a much clearer picture of how much water is being infiltrated into the garden. And then, as I said, the bacteria samples need to be processed within 6 hours of collection, so got some fun lab pictures for you. It can be cold and soggy work, but the students do love it, as proved by not only the number of volunteers that we have to do it, but the fact that people are willing to go out at 2 and 3 a.m. in the middle of the storm, because all of you know it only rains in the middle of the night, which is super fun. So the other part, in addition to measuring the flow, was actually measuring the pollutant concentrations and combining that into an actual mass load of the pollutants. So what we did was we took the concentration of an average one of the pollutants and these little 1-minute intervals, and so we split our hydrograph into 3 sections at the rise, the peak, and the fall of the storm. And then we multiply the flow data by the average concentration for that time, so we're able to get an average concentration of the rise, peak, and fall of the storm, so you can see how it changes. And then with that, obviously, you can add it and get an entire one mass for that pollutant for over the entire storm. And then you can also calculate the pollutant removal efficiency, so how much of that is being retained by the garden and not being put right back out into the creek and flowing into the wetlands and causing beach closures. So I'm going to show a couple pictures of hydrographs, and I wanted to put this up kind of first as a blown up picture so you guys can really see. Obviously the hydrographs are looking at flow over time, but the blue is the inflow and the orange is the outflow, and the really key aspect of these hydrographs is the difference between those 2 lines, because that means that all of that is being absorbed by the garden. So you don't need to really look at the numbers, just look at how far apart the lines are and how much of that water is really being retained by the garden. These are 2 storms from the first year on the left and 2 from the second year of the study on the right, including that February 17th monster storm where everyone was getting ready to build their ark. So as you can see, we were able to infiltrate an incredible amount of water. And this is a graph that's showing the relationship between the volume that was retained in the garden and the percent of the volume that was retained. So the average percent of flow that was retained was 91.8%. And the range was 75.4% to 100. And what that means is on our garden's worst day, it was still getting 3/4 of all the rain that was going through it, which is just incredible. And the range of the retained volumes on the right there, the 20,000 to over 1 million, that million was on that February 17th storm. These are some lab work photos, so I like to show people all the beautiful blue and the fecal indicator bacteria samples. It looks so nice, doesn't it? And to see the difference between the rise and the peak, the different tape on the orange cap vials, which are our metals, and the total suspended solids on the right side. So you can see at the rise, the water is looking a lot darker and grosser, basically, because there's a lot more suspended solids in there. So you can see what a difference throughout the storm that makes and how much is really going into the garden that's being retained there. So these are our mass removal efficiencies, and what I really want to point out is the average percent removal, so the number on the right side. You don't really need to look at the numbers on the graph unless you're super interested, but with time you probably won't really have a chance to look at it super closely. So the E. coli, we were getting 87.6% removal, and enterococci was 83.3%. This is another different version of the graph so that you can see the difference in concentration as well as mass, because we really wanted to also give the picture of looking at the concentration. So this is the percent difference in inlets and outlets. And what's really interesting about this is that you can get sometimes a higher concentration of the pollutant that you're looking at the outlet. And that kind of freaks people out, and that's why it's really critical to do the mass loading as opposed to only the concentration, because you're really not seeing the whole picture of what the garden is really doing. Okay, so total suspended solids, the average there was 86.5%. For our metals, we had 93.2% for copper, 92.3% for zinc, and then 92% for lead, which was actually pretty low, which was a really good sign. For diesel, we were getting 90.3%, 93.9% for motor oil, and for the polyaromatic hydrocarbons, we were seeing 89.9%. So these are our overall pollutant efficiencies, so you can see the difference between the inlets, the outlets, and then it's showing the mass that was retained and what's the percent of that. So conclusions, the garden is not only doing its job, it's doing an amazing job. We are getting greater than 75% of the flow that's going through there, depending on the nature of the storm. So depending on the intensity and the length of the storm, we're seeing 75 to 100% of the flow that's being retained in the garden. The average pollutant removal is 89.9%, which is phenomenal. Mass loading gets us a better picture than solely looking at concentration, as I said before, so it can make your numbers seem artificially higher if you're not looking at the overall mass. Something that I'm going to be working on in the coming year, I still have a year left in my program, so I am going to be working on building a regression model that builds a better picture of the relationship between the intensity of the storm, the length of the storm, and how much water is being retained, showing the picture of relationship between those. We also have a student from Cal State LA that's going to be looking at the fate of the metals that are sequestered in the garden, which I'm sure is kind of in the back of everyone's minds in these kinds of projects. So that's really the only thing that is questionable. Everything else should degrade over time. The metals, we are still researching that right now, but I do want to say that it would only be going back out into the creek, so it's not a complete, we're really keeping it from flowing out into the creek and affecting potential wildlife downstream. So hopefully it's not building up in the garden. Someone is looking into it to see if it's getting trapped in the plants, trapped in the soil, what percent of uptake is there. But I think that that's going to be a really interesting aspect of this study as well, because it's going to be in the exact same garden, so you can relate it right back to this exact same data. So I want to say thank you to everyone that helped with this project. And then this is a lovely picture after an entire night spent in the lab.